Hello viewers, welcome back to our series of lectures on chemical bonding. In today's session, we will continue our discussion on ionic solids. In the previous session, we talked about the structure of ionic solids. Now, today we will take up the defects in such ionic structures there. The session is planned as follows, that is, to begin with, we will briefly review the contents of previous sessions. Thereafter, we will see that what are lattice defects and then what is their importance. Having done that, we talk about different types of lattice defects, but basically try to classify the lattice defects there. Having done that, we come down to the point defects, because there are a number of types of lattice defects, but we will focus attention on to the point defects per se. And herein, we talk about different types of point defects, and they happen to be Schottky defect, Frankel defect, then there are color centers, and then other non-stoichiometric defects. We talk about in detail about all these different kinds of point defects there, and towards the end we will try to sum up what we do in today's session. Okay. Now, let us try to recall what we have done so far. What we have done so far is we basically discussed the classical and modern theories of chemical bonding in a number of lectures over there. Having done that, we came down to revisiting the basic aspects of crystalline solids, and thereafter we outlined the salient features of the structure of ionic solids that were did in the previous session. Thereafter, we described the characteristic structures for ionic solids of AX type, and having done that, we came down to the concept of radius ratio. We explained the rules called as radius ratio rules, and then saw that what are their applications and limitations over there. So, this is what we have done in the previous session. Let us recall that what we learnt in the solid state, that any crystalline solid has a highly ordered infinite lattice. That means, all the lattice positions there are occupied by either atoms, molecules or ions there, and we expect it to be a highly perfect system. However, such a perfect order exists only at 0 Kelvin. That is, as per the third law of thermodynamics. That means, a perfect crystalline solid can occur only at absolute 0 temperature, and which actually is not possible there. So, that means, in principle we do not have perfect crystalline solids ever. So, there are certain kind of imperfections there, and what you find is that typically all lattices, all crystalline solids at real temperatures, the temperature which we can come across, typically have got some kind of defects in them, and they are called as imperfections. So, there is no crystalline solid which is perfect. Okay. So, what kind of imperfections are there? And we find that these imperfections or defects in the lattices, they are called as lattice defects, and the number of such defects will depend on the temperature. That means, at absolute 0 there is no defect at all, it is perfect crystalline solid, which actually does not happen. As we move higher and higher in temperature, we find that there are more and more defects come into picture. And further, typically what we find is that any defect which is created in a crystalline solid, that actually increases the entropy of the solid. And also we know that for any defect to be created, we need certain amount of energy, and that energy which is required to create a defect actually is more than compensated by the resulting increase in entropy. And as a consequence, what we find is that all crystalline solids what we come across have got imperfections in them. Now, let us have a very interesting quote from Colin Humphrey, which says that crystals are like people, it is the defects in them which tend to make them interesting. That means, if everybody was to be alike, then world would be very different. What we find is that even human beings are not perfect, there are defects in them and which make them interesting and different from each other. Continuing to our crystalline solids there, we find that a pure diamond is colorless, but the impurities in diamonds, that is the one which impart them beautiful colors there. So, we find that these imperfections or impurities are actually very useful there, very important here. Okay. Now, in addition to this, because what we just mentioned, that all these defects are intrinsic, which are there by itself, but in addition to that, we can even introduce defects into the lattices to control or to alter the properties of the lattice there, or solid state, solid material there. One typical example is that of alloying. We know that brass is an alloy of copper and zinc. Pure copper has got certain structure, certain properties there, but when you alloy with zinc, the properties change. So, that means this brass happens to be much harder and stronger than the pure copper there. So, that means if I want to alter this property, the hardness of the metal here, I can alloy it with zinc here and get brass. So, that is, we are trying to introduce some kind of an impurity from outside or imperfection from outside and try to alter the property of the material there. Another example, we can even control the amount of impurities or the defects in a given crystalline solid to control the properties. One typical example happens to be that of semiconductors, about which we will be talking at a later stage in much details over there. We find that in semiconductors have got controlled amount of impurities, means we can control the amount of impurity in them and control thereby their conductivity. Further, we also know that the mechanical properties of steel depend on the type and amount of impurities in the iron, because we take iron and put different kind of impurities, we get variety of steels over there. Okay. So, the basic point which I want to bring home here is that is the impurities or the defects could be intrinsic, that is by nature itself, or they can be introduced from outside to augment or to control or to affect the properties of the solid state materials there. Okay. Now, let us try to see how do we classify defects there, these lattice defects. One basis could be the composition, and broadly on the basis of composition we can put these lattice defects into two groups. One happens to be stoichiometric defects. That means, as the name suggests, stoichiometry, that is the crystal composition is unchanged, that means their defects are there, but the stoichiometry of the crystal does not change. And second happens to be non-stoichiometric defects, wherein the composition of the material does change over there. That is one basic way of looking at the point other defects over there. Another way of looking at defects is on the basis of the size and shape. We can have point defects, as the name suggests, point, that means it involves only one atom or one site in the lattice there. Or we can have line defects, this is basically also called as dislocation defect. In this case what happens is one dimensional defect, that means in a lattice whole one a line, number of sites over there will be affected by the defect over there. Or we can have a plane or a boundary defect, wherein the whole layer in the crystal structure is defective over there. So, there are wide variety of lattice defects depending on the size and shape of the defect over there. That is another way of classifying them. Going further, there is another kind of defects we can think of, what we just mentioned earlier too, that is called as substitutional defects. That means defects which are introduced by substituting something from outside into the lattice there, and that is a foreign atom replaces the parent atom of the lattice and thus occupies its position. You can have situation of this kind. That means we had a lattice here wherein a given foreign atom has come and has replaced the given atom of the lattice there. This is called as a substitutional defect or an impurity there. Sometimes we can have a situation wherein that the foreign material comes and occupies some kind of an interstitial site over there. This is called as a interstitial impurity. This is called as substitutional impurity. That means this impurity is substituting one of the lattice sites of the original material, and in this case the impurity has gone, it does not replace anything from the original lattice, but it occupies some kind of an interstitial site, that is a void in the lattice there. Okay. Now, the substitution atom is of the same size or slightly smaller or greater than that of the parent atom. Depending on that, it can either occupy, it can replace the atom there, or it can occupy interstitial, and accordingly it will lead to some kind of a distortion in the lattice over there. Now, let us come down to the point defects. What are point defects? Let us see. As we just mentioned earlier too, these are defects, as the name also suggests, defects associated with one or two atomic positions. That means some points in the lattice are getting affected over there, and these arise because of two reasons there. One, the one possibility of points defects coming into picture is, that is when the crystallization is taking place, when the crystal is being formed or the lattice is being created, there could be the packing defects are there. That means when they are packing together, something is left in between. So, you can have defects coming intrinsically in the process of formation of the crystal there. Another possibility, in this case there are two varieties there. One is called as a vacancy, and one is called as interstitial, or common types of point defects there. Vacancy is, that means when the lattice is being formed, some position remains vacant, it is not occupied and the crystal builds on thereafter. Or sometimes what happens is an atom is coming or an ion is coming, that does not occupy the lattice position, but gets into the interstitial there. So, there are two typical common types of point defects, what is called as a vacancy and interstitial. Vacancy is one position is not occupied, interstitial is something has gone interstitial within the lattice over there. Okay. Now, vacancy is the simplest point defect, and this can arise from one, as I just mentioned, imperfect packing during the original crystallization, or because of thermal vibrations of the atoms at higher temperatures. What can happen is, we got a lattice at a low temperature, okay, everything is in order to a good extent, but if the temperature increases, the atoms are not stationary, they are vibrating at their positions. It may so happen that because of this energy coming from the temperature, some atoms might come out of their positions and then create a vacancy over there. So, that is how a vacancy can be created. One is in the process of crystallization, second is because of thermal vibrations. Further, vacancies may be single or divalency or a divacancy or a trivacancy obtained by combination. That means, what it means is the following, that means we have got a crystal lattice, there is one vacancy there. It may be so that there is another vacancy there, and it may so happen that there are two vacancies come too close, and they what is called as a divacancy. That means, this vacancy is there, some atom moves from here, the vacancy comes here, then something comes from here. We will talk about it as we move further. That means, the two vacancies come close vicinity of each other, that is called as a divacancy, and so on and so forth. Now, the atoms surrounding vacancies tend to be closer, thereby distorting the lattice point. It is very, very important. Now, you just imagine that we got a lattice over there, and one atom has been lost from there. So, what will happen is, so this position there, so the atoms which are surrounding this vacancy will be having more space to move around. As a consequence, that will kind of distort the lattice plane, and that is lead to some kind of a imperfection into the crystalline solid there. The interstitials. Interstitials are obtained when extra atom is lodged within the crystal structure, as we mentioned earlier too, and it is observed in crystals with low atomic packing factor there. I mean, the packing is not very large, so this kind of interstitial defects are observed in that crystals more often. And light vacancies, where interstitials may also be single, di-interstitials or tri-interstitials, a similar pattern will hold here too. Okay. So, this is general about point defects. Let us see that one very interesting point here is that the vacancy and interstitial are inverse phenomena. In case of vacancy, something is lost from a given common kind of normal site of the lattice there, and in case of interstitial, something has gone within the different lattice sites over there. So, there are two inverse phenomena. Okay. Now, let us see what are different types of point defects, and we will talk about each of them in details here. Different types of point defects are Schottky defect, and second one happens to be Frankel defect. Then we got what are called as color centers, and then there are other color centers also are non-stoichiometric, because these are stoichiometric defects, and this happens to be a non-stoichiometric, and there are certain other non-stoichiometric defects. We will talk about all these defects one by one. Let us start by Schottky defect. Schottky defects basically they consist of a pair of vacant sites, an anion vacancy and a cation vacancy. So, what do we have is, we have got a lattice here, and what you find is there are two vacancies there. One is an anion vacancy, the blue sphere here is a cation, and this one happens to be an anion, and so on and so forth. So, we find that we have a position which was expected to be occupied by an anion, but that happens to be vacant. So, this is an anion vacancy. Similarly, we got a cation vacancy here. So, and this kind of a defect is observed in ionic solids like halides, sodium chloride is typical example, or some oxides over there. Now, these vacancies are compensated by two extra atoms at the surface of the crystal. That means, suppose this lattice is formed there and these two are vacancies there. So, these two atoms will be found somewhere here over there. That means, the overall stoichiometry does not change. The only thing is, some sites in the lattice are unoccupied. So, they are vacant sites there, and some of them happen to be anion, some of them happen to be cation vacancies, and the two will be equal. Let us go further. Let us look at the characteristics of Schottky defect. So, there are equal number of anion and cation vacancies, because overall our ionic solid happens to be electroneutral. Now, what we see is that in any lattice, the number of lattice positions are enormous. It runs into 10 to the power 20, 21 and so on and so forth. The number is too big, and the number of vacancies also are fairly large, and these vacancies are distributed randomly amongst these things. It is not that all vacancies will be in one pocket over there. No, they are distributed randomly throughout the lattice over there. Further, some of these vacancies may associate to form ion pairs or clusters. That is, we can have a situation that there is a cation vacancy and an anion vacancy. So, the two are close by, they form an ion pair there, or they can add further to form what is called as clusters there. Then this is important here, because in case of Schottky defects, since there are vacancies, so we find that the density will decrease, because the volume remains the same, but certain atoms or the ions are missing from there. So, the mass becomes less. As a consequence, the density decreases there. And typically in a crystal, say, of sodium chloride, we find that 1 in 10 to 15 anion and cation sites are there as vacant at room temperature. So, that means that gives an idea about the number of vacancies what we have. Suppose I talk about 1 mole of this will come to about 10 to the power 8, because this will be 10 to the power 23, this will become 10 to the power 8. So, there are about 10 to the power 8 vacancies in 1 mole of sodium chloride. Now, that is a fairly large number. Now, let us move on to the Frankel defects. In case of Frankel defects, basically they involve displacement of an atom from its lattice site into an interstitial site. Very interesting phenomenon. Let us look at this. So, basically what happens is, we have got a lattice there, and from the lattice a given, say in this case what I am showing here is, this is a cation here, which actually has moved from its own position and got into an interstitial there. So, such a thing happening, that means we have got a cation vacancy and a cation as interstitial there. So, such kind of a defect is referred to as Frankel defect. So, this basically Frankel defect essentially constitutes a vacancy interstitial pair, and silver chloride having structure of sodium chloride structure is a typical example there. Let us understand this. So, this is a typical sodium chloride structure here, and what you find is these white spheres here are the silver ions in this, and typically the silver ion here. So, at this octahedral void here, which is the position for silver ion here, actually what happens is, in case of Frankel defect, the silver ion from this octahedral void here, right in the center of this cube here, that moves to this position here, which happens to be a tetrahedral void. So, and what happens as a consequence is that this position becomes vacant here. This is a cation vacancy now, and this position, which was actually interstitial, is occupied by the silver cation there. So, such a defect is called as Frankel defect. That is, the silver ion moves from the octahedral void into a tetrahedral void. Tetrahedral void happens to be interstitial position. Octahedral void was its original position, which actually now becomes a cation vacancy. Okay. So, like Schottky's defect, this may also form ion pairs. That is a possibility that two such defects can come closer to each other. But in this case, what we find is the number of atoms or ions do not change. It is just that one particular atom, a cation, has moved from one place to another place there. So, the overall density will not change, because the mass has not changed. In case of Schottky defect, what we had was some sites were totally missing. So, the mass was not there, volume was there. So, in this case, the mass and volume do not change. As a consequence, the density does not change for Frankel defects there. Okay, let us move further and come down to what is called as colored centers. Colored centers basically are non-stoichiometric defects, and typically have got metal excess. This is a very interesting class of defects what we have. So, actually what happens is, historically Becquerel actually discovered that sodium chloride crystal, which happens to be transparent, when was placed near a discharge tube, it was observed to become yellowish, and we know that a perfect NaCl crystal should not be absorbing any visible light. That means, it is expected to be transparent, but it was becoming yellowish. That means, it has to be attributed to some kind of a defects in the crystal. That means, by placing it close to the discharge tube, some kind of defects have come into the crystal of sodium chloride, and such defects which make the crystal colored are called as colored centers there. Let us talk in detail about this. In case of colored centers, basically we can define a colored center to be a defect in crystalline solid that makes it absorb visible IR or UV radiation and impart some kind of a characteristic color to this. So, that is very important. That is why the name, the colored centers there. Further, most common color center happens to be what is called as F center. This F center has been, this term has been coined from this word, which is a German word called as Farbencenter. That means color bearing center over there. And typically an F center actually is nothing but a point defect having an electron trapped in an anion vacancy. That means we have got an anion vacancy and an electron occupies that. Such a situation is referred to as F center there. And this anion vacancy where the electron is captured there is basically acting as a positively charged particle which attracts the electron towards itself and traps it, and that electron trapped into an anion vacancy is an F center there, and that is what is responsible for the color of the material. We will look into this. Now, look at this. So, this is my crystal of sodium chloride here, and what you find is that here we have got an anion vacancy because these blue are cations there. So, this is a position for an anion to be occupied, which actually is missing, and instead of the anion there, an electron has been trapped in this, and because of this electron here, this material, the sodium chloride, the sample of sodium chloride of this kind has yellow color there. And how do we prepare such a sample is, that is what we do is we take an alkali halide, say sodium chloride, and heat it in the vapors of alkali metal, say in this case we take sodium vapor only. So, when we do this, we find that we get a new compound having the following formulation, that means Na to be equal to 1 plus delta. Delta means a very small number. That means the ratio of sodium ion to chloride ion is not 1:1, it is slightly more than 1 sodium ion per chloride ion over there. That means this becomes a some kind of a non-stoichiometric effect over there. Okay. Now, let us see how an F center is formed. Look at this. Typically, what we have is we have got a crystal of sodium chloride here and having an anion vacancy. Okay. And we take this sample of sodium chloride, heat in presence of sodium vapors, and some of the vapors get adsorbed onto the sample of lattice over there. This is my sodium chloride lattice there, because this blue are my sodium ions and the other ones are the chloride ions over there. Now, this is my sodium atom which has got adsorbed onto the lattice there. Now, what happens is this sodium atom ionizes to give me a sodium ion and an electron. That is my step 1. The first step is actually adsorption here. The second step is ionization of sodium atom to give me a sodium ion and a free electron there. And then this free electron actually moves along the crystal and gets into an anion vacancy over there. And then thereafter, so what we have is we have got an electron trapped into an anion vacancy, but simultaneously what happens is there is an anion elsewhere. This anion will move and try to come out over here, and as a consequence what you get is we get an anion vacancy here, and we have got a sodium chloride over there. That means this is my sodium ion, this is my chloride ion which has moved from here to here there. So, and then this is my F center wherein the electron has been captured into an anion vacancy there, and this is the material which is giving me color there. And how does it give color? Let us see that. This, the electron which has been trapped into an anion vacancy actually acts as an electron in a box. Typically, you must have heard about, must have learnt about a quantum mechanical system that is called as particle in a box. It is similar to that, and since it is electron in a box, what you have is this electron has got possible quantized energy levels over there, and when we give energy to this system, that means when you give show some light on this, what happens is because of absorption of radiation there are transitions among these energy levels, and as a consequence the material becomes colored. So, essentially an F center can be visualized as an electron trapped into an anion vacancy, and this electron has available to it number of quantized energy levels, and when we give radiation to that, part of the visible radiation is absorbed, and as a consequence this material becomes colored. Okay. Now, let us look at some typical observations regarding F centers there. The color which is observed for F center, because we said F center can be created by taking any alkali halide and alkali vapor there. So, we can have what we took the example as sodium chloride and sodium vapor there. We can have say lithium fluoride and lithium vapor, we find that we get pink color, or if we take KCl and potassium vapors, we get blue color there. And that means the color which will be produced will depend on the nature of the crystal there. So, in this case lithium fluoride, here we got KCl, so we got different kind of colors coming. For sodium chloride we are getting a yellow color there. Further, the color observed actually depends on the host crystal and not on the source of the electron. What we can do is, we can take sodium chloride, but do not heat it with sodium vapors, but do it with the potassium vapors. And here again what you find is, we still get the same yellowish coloration. That means, the color will not depend on the source of electron, but on the basic lattice what you are trying to use over there, the basic material which is being used over there. That is very interesting experimental observation about F centers there. Okay. Now, F centers actually can be formed another way. One of the another ways of doing it is by irradiating the alkali halides with a source of ionizing radiation, like a Tesla coil or an X-ray radiation there. So, in this case what happens is, because that what we discussed earlier was one mechanism, that means we take alkali metal, alkali halide and heat it with the vapors of alkali metal there, and in this process we can get one some kind of F centers over there. Second way of doing it is by irradiating the alkali halide with some kind of a very strong radiation like Tesla coil or an X-rays. Now, in this case, this is one typical demonstration here. That means we got in this test tube, there are certain crystals over there, and these crystals are being irradiated by some kind of a Tesla coil, which gives you high energy radiation there. And as a consequence, we find is that we get, if I take sodium chloride crystal, we can get a yellowish material there. For KCl, we get this coloration, and for KBr, a different coloration is there. So, essentially, what you are getting is, that is an alkali halide when irradiated with the high energy radiation, we can get these defects over there. But the mechanism of defect formation in such cases happen to be different. So, the F centers produced by radiation actually have got different mechanism. The ionizing radiation actually causes the halide ions to lose an electron to produce a halogen atom. That means, we got a halide ion, because there are sodium say alkali metal ion, halide ion there. So, halide ion loses an electron, becomes an halogen atom there, and this halogen atom, that means the electron which has gone from this for the first step there, that moves through the crystal and occupies a halide vacancy, and the halogen atom then interacts with a halide ion to form a molecular ion called as Cl2 minus, and this electron again which is into a halide vacancy, that is responsible for the color of the material. So, in this case the mechanism happens to be different from what we had in the previous case there. Now, let us look at some other type of F centers there. This is called as Fa center. So, in this case, this is similar to what we had in the previous case of F center. F center was an electron trapped into an anion vacancy, but in this case what you see is that we have got an electron trapped into an anion vacancy, but also we have got a substitutional defect over there. That means, sodium ion has been substituted by a lithium ion there. So, such a situation is referred to as an Fa center. The different, because it will have a different kind of behavior, the material will have a different behavior altogether. Another possibility is Fb center. We may have a situation where there is an electron trapped into an anion vacancy, and there are two neighboring cation positions are occupied by kind of alkali metal ion of different alkali metal there, lithium ions in place of sodium ions over there. Okay. Third possibility is F2 centers. This is again very interesting. It may so happen that two F centers, they come close to each other. Such a situation, that means there are two electrons trapped into neighboring anion vacancies, or this situation is referred to as an F2 center. Now, let us move on to some other type of non-stoichiometric defects, and we will take up two typical examples, one of metal excess, and the most common example is that of zinc oxide. We know that zinc oxide happens to be white at room temperature, but when we heat it, it turns yellow, and that happens because of the following thing. That means, in this case what the material what we get actually is a non-stoichiometric material, which has a formula as ZnYO, where Y happens to be greater than 1. That means, there are more of zinc ions than oxygen ions over there, and what basically happens is, on heating zinc oxide, it loses oxygen. That means, oxide ions actually they give oxygen out, and what we get is we get zinc ions and electrons over there. And in this representation here, this green spheres are representing oxide ions there, and this red spheres are representing the zinc ions there. So what happens is, when this happens, when oxygen is lost, so what will happen is there will be an excess of zinc ions than oxide ions. Initially, to begin with, we had got 1:1 zinc ions and oxide ions there, but because some of the oxides has been converted into oxygen, we get a shortage of oxygen oxide ions over there. So there is an excess of zinc ions. So these excess zinc ions and electron, they move on to neighboring interstitial sites over there. So what you find is that this zinc ion has got into an interstitial site over there, because we had the zinc oxide over here. Oxygen has been lost and we got a zinc ion. The zinc ion now doesn't stay there, it moves into an interstitial there, and the electrons what we get here as a consequence of this reaction over there, so they also occupy the interstitial sites over there. So such a material also are colored, and this is again a kind of a non-stoichiometric defect there. Now let us move on to another kind of non-stoichiometric defect, what is called as metal deficiency defect. In the previous case we got metal excess there. Now the typical example is that of ferrous oxide. Ferrous oxide, when heated in oxygen atmosphere, this gives us the following composition FeXO, where X happens to be less than 1. That means there are lesser iron as against the oxide ions over there. And typically, structurally speaking, that is how do we represent that. And what basically happens is that when we heat in presence of oxygen, some of the ferrous ions, they get oxidized to ferric ions there, and that is how do we represent that. That means 2 ferric ions will get oxidized to 2 ferrous ions will get oxidized to 2 ferric ions there, and 2 electrons will be released over there. Now since there is an excess of oxygen now in this formulation there, so that means it in turn it implies that there will be cation vacancies. Some of the cation positions will be empty over there. Now in order to maintain electron neutrality, what basically happens is these ferric ions there, so they occupy 2 of the cation positions there, and this cation vacancy is created over there. That is, these 2 into 3 will give me 6 charges there, 6 positive, and earlier what we had was we got ferrous ion here, ferrous ion here, ferrous ion here. So we got 3 ferrous ions and having charge of 6 plus 6 positive charges. Now we got only 2 ferric ions there and having the equivalent number of charge, and that charge balance will come into picture there. So this is a typical example of a non-stoichiometric defect with metal deficiency there. Okay, let us quickly sum up what we have done today. We basically reviewed the contents of previous sessions, and then thereafter we defined what are lattice defects and outlined their importance. Having done that, we moved on to discussing different types of lattices. Basically we classified lattice defects, and then thereafter we discussed different types of point defects and their characteristics. Now in the next session we will move on to what is called as metallic bonding. That means what kind of bonding is there in case of metals there. Thank you.